In this video, we're going to dive into section 14.5, which is on polyprotic acids. So there's the learning outcomes and expectations. Feel free to pause and read through those. Yeah, diving into 14.5, polyprotic acids. You'll note we skipped section 14.4, hydrolysis of salt solutions. For the sake of time, we're not going to dive into that. The general idea is salts can be acidic or basic or neutral, depending on the nature of the species involved in the salt. But yeah, we're going to skip over that, and we're going to dive right into 14.5, which is polyprotic acids. And so everything we've talked about so far is a monoprotic acid. And so when comparing mono and polyprotic acids, it's exactly what it sounds like. Like going back to Latin roots, mono means one, poly means many. And so for a monoprotic acid, it is a species that only donates one proton per molecule. And so something like HCl, it donates one H+. HNO3 donates one H+. Vinegar acetic acid donates one H+, at least under normal conditions. Polyprotic acid, on the other hand, can donate more than one proton per molecule. And so H2OSO4 is a diprotic acid where it can donate one proton, and then it can donate a second proton. Similarly, you have phosphonic acid. In this case, it can donate three protons. First proton, second proton, third proton. And that's what makes them polyprotic, because there's more than one proton. And so polyprotic acids, again, they can donate more than one proton, but one of the keys of polyprotic acids is, at least with most of them, they don't donate all three of them at the same time, or all two of them at the same time. They do so in a stepwise manner, and because of that, they have an equilibrium constant associated with each step. And so looking at carbonic acid here, this is H2CO3. There you can see the structure. It's essentially a mirror of two carboxylic acid groups. And so this guy can donate one proton here to give you HCO3-. That's the conjugate base. But this conjugate base still has an acidic group. And so this can act as an acid. And so we can draw another equation where that acid gives up a proton to give the conjugate base. And so that's what it means to be polyprotic. Gives up one proton. The conjugate base can still give up another proton. So now it's an acid in the next step. And then it gives up that proton to generate the conjugate base. And so one of the keys to this multi-step process is we can draw an equilibrium or write an equilibrium constant expression for each one of these. We can say products over reactants, that's Ka. We have products over reactants, that's Ka. The difference between these two is we write a Ka1 for the first step and a Ka2 for the second step. This basically denotes, hey, this is the first step of proton dissociation. This is the second step. And so you have reactants products over reactants gives you this. Reactants products over reactants gives you this. And so Ka1, Ka2. And so you can look at tabulated values for all these various polyprotic acids. This is sulfuric acid. It gives up its first proton to become this, the hydrogen sulfate ion. This one is a strong acid. This one's a much weaker acid. So there's a very large Ka value. That's a much smaller Ka value. Similar to oxalic acid gives up a proton. It becomes this. This one can still give up another proton, but it's a much weaker acid. And so across this binary and ternary acids, the strength decreases as the H+ is released, and so it's harder and harder to give up each subsequent H+ atom. And basically, you can see this in the Ka. The Ka becomes smaller as it gives up those protons, and so going from the first proton to the second proton, the Ka becomes smaller. It's a weaker acid. So each step it gives up, it is a weaker acid. It is less willing to give up the subsequent protons by each step. And so one important thing about this is even though it can give up protons, more often than not, because you can see this is a 3 order of magnitude difference, it's really only the first step that primarily dictates the pH of the solution. Really, the second step, it can give up protons, but you can see it's going to give it up 1,000 times less than the first step will. And so for the most part, although it gives up multiple protons, the first proton is typically going to dictate the pH of the solution, at least if you start with this guy. If you start with this one, obviously the second proton will dictate what's going to happen. And so each one of the steps, there's an equilibrium. And something important to note about equilibrium, even if your K value is very large or very small, there's still an equilibrium. And so all those species exist simultaneously. And so in going back to this mixture, this Ka is going to be it's going to be 3 orders of magnitude larger than this one. And so this is going to be the primary equilibrium generating these species. But all of these species are present in solution. It's just a question of how much there's going to be of each of those. And so when talking about Ka values, we're gonna harken back to our pH calculation. If you guys remember, we use a pH scale not because it changes the numbers or anything, at least not in a absolute way. They're still related. All it does is make them more convenient to deal with. And so negative log of H3O plus gives us our pH value. And so it's much more convenient to talk about pH 4.5 than it is to talk about 2.8 times 10 to the minus 5. Something similar is true with Ka values. And so rather than talk about things in terms of Ka values, what we commonly see, and this is particularly in organic and biochemistry, we'll talk about pKa values. And just like Ka, or just like pH and pOH and pKw we talked about previously, all that is the negative log of Ka. So if you take the negative log of Ka, that gives you the pKa value. And so pKa value puts it on a nice and convenient scale. Not only that, it allows us to relate this Ka value to the pH of the solution via this pKa value. And I'll explain what that means in a bit. But the take home for you guys is essentially, we have a Ka value. The larger the Ka, the stronger the acid. The smaller the Ka, the weaker the acid. We can take a negative log of this, which gives us this convenient scale. The smaller that number, the stronger the acid. The larger that number, the weaker the acid. And so pKa gives us a really convenient, scale to start talking about these numbers. And so the reason we do this is so we can compare to the pH of the solution. And so the reason we want to do this is we want to predict what the dominant form is in solution. And so if you take something like vinegar or acetic acid, the pKa, the negative log of the K, is 4.76. So that basically tells you a really nice number. Here's how strong acetic acid is. And so you can think about solutions. You're throwing this acid in a solution, right? And you could throw it in a solution that has a pH less than 4.76, a pH greater than 4.76, or a pH equal to 4.76. And so we can think about the solution of the pH of the solution is already fixed. You're going to add acetic acid to it, and you want to know which one of these is the dominant species. Well, this number right here is going to tell us that. And so if the pH is less than pKa, it basically tells you that the solution is a stronger acid than acetic acid. It says there's already a whole bunch of protons floating around. It doesn't need additional protons from acetic acid. In fact, it doesn't want them because this is not a stronger acid than the solution. So basically what happens in a solution where the pH is greater than the pKa, in this case the pKa is 4.76, it is going to primarily exist in its acetic form. And so you can think about this looking back at Le Chatelier's principle. If pH is less than pKa, it means this H plus concentration is high, which means it's shifting this equilibrium this direction. And so that's exactly what's happening, right? The external solution is more acidic. It has more H pluses than it needs, or at least relative to acetic acid. So it's forcing this guy to stay protonated. If we put it in this basic solution, right, where the pH is greater than 4.76, and it's not even basic, it's just more basic than 4.76, it basically says this acetic acid is a stronger acid than the surrounding solution. And so what that means is it's willing to give up its H plus to the surrounding solution. And so the dominant form, when the pH of the solution is greater than 4.76, is going to be the conjugate base. Basically says the surrounding doesn't have more H pluses, and so this goes down, it shifts it right, it wants to be this dominant form. At pH 4.76, turns out you're going to have a 50-50 mixture of the two. So essentially pH is equal to pKa, HA equals A minus. We'll get back to this when we talk about Henderson-Hasselbalch equation, but it's saying when your pH equals pKa, you have a 50-50 mixture. If the pH is greater than the pKa, the pH of the solution is more basic than the thing you're adding, it's going to give up its protons. If the pH of the surrounding solution is more acidic than what you're adding, it's going to keep its protons. And so we can predict the protonation state based on the relationship between pH and pKa. And so this can get complex, especially with polyprotic acids. And so this is just a monoprotic acid. We're only giving up and taking one proton. If you have a polyprotic acid, you have one Ka value or pKa value. You have another one. You have another one. Each one of these steps. And so you can think about a spectrum of species that exist where you're at high pH, where the solution is basic, it wants to steal protons from this molecule, or you can think about a low pH solution where it doesn't want to steal protons. And so you have this range of values, 2.1, 7.2, 12.3. So it basically tells you If the pH is less than 2.1, it says the solution is stronger than every one of these steps. It basically says there's H+, all these are shifting to the left. The most favorable species is going to be the fully protonated one. It says when there's a battle between the acidity of the solution and the acidity of the molecule, if the solution's pH is lower than the pKa, the solution wins, and it's going to push its protons onto that molecule, and H3PO4 will be the dominant species. But if we go above 2.1, it basically says, okay, it says this is a stronger acid than the external solution, but this is a weaker acid than the external solution. And so this one won't go this way, this one will go this way. And so your dominant species will be this H2PO4. If you go even higher pH, let's say you go above this 7.2 threshold, and so the solution is less acidic than this guy, but more acidic than this guy, it says the dominant form is going to be this HPO4 2-. Likewise, if you go and have a high pH solution, basically the solution is more basic than all of these, pH is greater than pKa of all of these, it says it's going to take away protons from everything, including each one of these molecules. This goes down, it shifts it right, shifts it right, shifts it right. You're going to be dominated by this PO4 3-. And so it basically tells us which one of these species are going to exist. And there's going to be thresholds along the way. And in between each one of these thresholds, we're going to have a 50-50 mixture of two species along the way. And so when I recommend thinking about this, first start with this example and then justify to yourself, why does it want to be protonated here? Why is it deprotonated here? And you're essentially applying that same thinking to each step in this process here. And so that's how we make a prediction about which protonation state is going to exist based on the pH versus the pKa. There's there's other classes of polyprotic acids, and so that one was where basically the OH group was previously we talked about the OH group being attached to a central atom. You can have other polyprotic acids, and one example is polypeptides and proteins, where you can have an N-terminus and the C-terminus. In this case, the C-terminus is a carboxylic acid or a carboxylate. The N-terminus is an amine group that can be protonated or deprotonated. Not only that, but each one of these side chains on amino acids, they can also have acid groups. And so if you look at each of these, there's a carboxylic acid, there's your amine terminus there, carboxylic acid, amine, carboxylic acid, amine. Each one of these guys has an NH3. You can see these NH2 groups over here. You can see OH groups, which are also acidic, SH groups, NH2, which can donate or accept a proton. And so the take-home message is amino acids and proteins, they are polyprotic acids. They can accept or donate protons depending on what the surrounding environment is. But one thing about these is that, for the most part, these acid and base groups don't behave cooperatively. They kind of behave independently of each other. And the reason is, when we talked about these previous species where you can see the OH groups are in close proximity, they're all attached to this phosphorus atom. These guys are sufficiently separated that what happens here doesn't really affect what's happening here. And so polypeptides, for the most part, the Kas of each individual group are independent. It doesn't mean it's increasing with each proton or anything like that. It just means they're going to have different pKas. But all these values, it turns out, is known. And so if you look at the list of all naturally occurring amino acids, you have a pK1, pK2. pKa1 is the carboxylic group, pKa2 is the amine group, and sometimes they have a pKa3 or a pKr. R in this case represents whatever the side chain is coming off here. And so you can actually find out how strong this acid is, how strong this acid is, how strong the R group associated here is. And so much like we did with the acetic acid and the phosphoric acid, we can predict what the protonation state is going to be based on the Ka values of these different groups. And so the pKa of carboxylic acid in this case is 2.3. The pKa of the amine group is going to be 9.7. And so it basically tells us we got to think back to, is the external solution more acidic than this or less acidic than this? And so here you can see the spectrum of possible pHs. We're going to go from 0 to 14. We have two important values here, 2.3, which is the threshold for this protonating or deprotonating, and we have 9.7, which is the threshold for this amine group here, protonating or deprotonating. And so if we start off on this end here at a pH of 0, in fact, anything less than 2.3, you have a very acidic solution. And what this number tells you is that the external solution is more acidic than this, it's more acidic than this, which means both of these groups are going to be protonated. And that's exactly what you see here, H3N, COOH. Let's go to the other end of the spectrum where you have a basic solution at, say, pH 14. It says the external solution is much more basic than this molecule, and you know that because the pH is greater than the pKa. And so it basically says the external solution is going to win. It's going to steal protons from this. It's going to steal protons from this, and you're going to have the fully deprotonated form. And so you have COOH minus, which is the conjugate of the COOH, and you have NH2, which is the conjugate of NH3 plus. And so under basic conditions, the solution wins, it steals all those protons. Under acidic conditions, the solution wins in terms of donating those protons, it keeps this molecule protonated. And so it really comes down to, is the solution more basic or is it more acidic? And so there's a middle ground condition here. You can see between 2.3 and 9.7, the pH of the solution is going to do different things to the different groups, right? And so if the pH gets to be larger than 2.3, it says the external solution is more basic than the molecule. It's going to steal its protons from the COOH group. But the NH3 group doesn't give up its protons as easily. And so anywhere between 2.3 and 9.7, it basically says the external solution is strong enough to steal a proton from the COOH, but not strong enough to steal it from the NH3. And so you only lose one of those two protons. And so this is known as the Zwitter ion. It's a balancing plus and minus. Under biological conditions, most amino acids exist in this condition here because it's between this 2.3 and 9.7 range. And so yeah, take home, you're thinking about how strong is the external solution compared to the molecule you're putting into it. If it's more basic, it pulls all the protons off. If it's less basic, it's more acidic, it's going to force those protons to be on the molecule. And then there's a middle ground where it can deprotonate some groups but protonate other groups. And so that's the kind of prediction you're making. All right, so to close out polyprotic acid, some molecules can donate and accept more than one proton. They're known as polyprotic acids. Basically, you have an acid, it gives up a proton, you make a conjugate base. That conjugate base can give up another proton, which means it's an acid for the next step and dissociates to give you H plus the conjugate base. And so we talked about the strength of each step. And so for these binary and ternary acids that we talked about in the previous PowerPoint, the acid strength decreases as it gives up each proton, and the pH of the solution is predominantly driven by that first proton. The other thing we talked about is pKa's. That's the negative log of the Ka value. It's a really convenient number because it allows us to compare pH and pKa. And so we basically say, okay, if pH is lower than pKa, it's not going to steal that proton. It's going to keep the proton in the molecule. If the pH is greater than pKa, the solution is more basic than the molecule, it's going to steal that proton. And so we can make predictions about protonation states of amino acids, of polyprotic acids of any kind. We can tell you which one's protonated and which one's deprotonated based on the pKa versus the pH values. All right, so that closes out polyprotic acids. Next, we're going to dive into buffer solutions.